Hello everyone. In this class we will discuss about the digital to analog converters using ladder method. So why we need this kind of data converters? So in the real world most data are available in the form of analog in nature and we have to convert that one analog to digital in order to process using a computer. For example, when you are recording your voice signals, it has to be your input signal is in analog form, and for processing for communication purpose, this has to be processed. So for that, it will be converted into a digital world. While the transmission is completed on the receiver end, it has to be converted back to from digital to analog conversion. So this kind of things are very much necessary in digital electronics. So there are different methods to convert from analog to digital as well as from digital to analog. So in this class, we will discuss about the digital to analog conversions, where we will convert the data available in the digital world, that is in the form of zeros and ones, into analog data. So what is a digital to analog converter? So a digital to analog converter which converts a digital signals to corresponding analog output voltage or output current. So these are our digital inputs that are in the form of ones and zeros. This has to be converted using suitable converter so that you will get corresponding signals, that is the analog signals. So this is the one of the block diagram of a digital to analog converter, where these are our input digital signals. These are D0, D1, D2, etc. until Dn, and this is converted into analog voltage. So in order to convert that, we need to give some reference voltage. This will be converted, the output voltage will be converted using the weighted average, that is by divided by 2 method. So this is what is meant by a digital to analog converter. So in a digital to analog converter, there are different parameters which we need to consider. These are the reference voltage, the resolution, the linearity or conversion, the speed at which the conversion is processed, the settling time, and error. The resolution is the amount of voltage rise created by increasing the least significant bit of the input by 1. So this is the voltage value which corresponds to the which is the corresponding increasing voltage in the output by when we are increasing the least significant bit by 1 unit. So this voltage value is a function of the number of input bits and the reference voltage. So the resolution of a digital to analog converter can be calculated using this method, that is equal to the reference voltage divided by 2 raised to n bits. So depending on the number of bit which we are using. And the linearity is the relation between the output voltage and the digital signal input. So here you can see on the x-axis, that is the digital input which we need to convert it into corresponding output analog values. So these are in the unit of zeros and ones, and this is the corresponding analog value. The speed at which the conversion is processed are usually specified as the conversion rate or the sampling rate, or it is the rate at which the input register is cycled through the digital to analog converter. So normally for a high speed digital to analog converter, the speed is specified as 1 megahertz, and it will depend on the speed of the digital to analog conversion will definitely will be depend on the clock speed. So if you are increasing the clock speed, we can increase it. It will also depending on the settling time of the digital to analog converter. So the settling time which is defined as the time for converter output to stabilize within the half least significant bit. So ideally, a digital to analog converter would instantaneously change its output value when the digital input is changing. In a real world, in a real digital to analog converter, it takes some time for the digital to analog converter to reach the actual output value. So that is called the settling time. So this is our input signal. We are converting the input signal into analog value. So this is the expected value, but initially it is increasing somehow, and it is going to lower than of least significant bit. But after some times, after a time that is called settling time, this value will be within the expected value by a change of one least significant bit. So plus half LSB and between plus half LSB and minus half LSB. Now we can say that the conversion is completed. So it takes some time to convert. So that is called the settling time. There are two type of digital to analog converters, which are the weighted resistor digital to analog converter and R2R ladder type digital to analog converter. So in your syllabus, we only need to study about the R2R ladder digital to analog converter, but we need to discuss what is meant by the weighted resistor digital to analog converter. So this is diagram of a binary weighted digital to analog converter. So you can see that this is our reference voltage which is given to this terminal, and this is the output voltage here. So a weighted resistor digital to analog converter produces an analog output which is almost equal to the digital input by using binary weighted resistors in the input adder circuit. So here you can see that this is an adder circuit. So this is an op-amp based adder circuit where the resistor, the first resistor is R, and the second one is 2R and 4R and so on. So this is increasing in binary order, so that the current at this point will be some value I1, and at this point it will be divided by 2, and this point it will be divided by 4 and so on. So we are arranging resistors in a increasing order of binary values, so that we can say this is corresponds to the most significant bit. So this is the most significant bit, and this is the second most significant bit, and so on, and this is the least significant bit. So whenever we are connecting one data into the most significant bit, so whenever this is high, we directly connect this value to the V reference, that is the reference voltage. Whenever that value is 0, we connect that one to the ground. So each of this data will be connected either to the reference voltage or to the ground, depending on the input value is high or low. So this will be the corresponding output value, that is V out is equal to minus RF. So this is the output of a summing amplifier using op-amp. So that is the feedback resistor minus of RF into V1 by R plus V2 by 2R, because this resistance is 2R, and V3 by 4R and so on. So this is how we will get some output voltage which is corresponds to the digital input which we are giving here. So digital inputs are ones and zeros. So 1 means that is the connected to the reference voltage, and 0 corresponds to when we are connecting to the ground terminal. So this is how a binary weighted resistor works. So the drawback of this type of converter is because we have to identify correct resistors. So if you are using some many bit resistors, we have to get corresponding resistor value in this order, and it is very difficult to get the different resistor value in increasing exactly double values. Also, if there is a difference between the resistor value corresponds to the least significant and most significant bit, which will increase as the number of bits present in the digital input increases. It is very difficult to, that is the most important thing, it is very difficult to design accurate resistors in order to get corresponding output values. Hence we need to look into different type of design, that is the R2R ladder digital to analog converter. So as it specified, instead of using R, 2R, 4R, etc., different type of resistors, in this network we will use only two type of resistors, one is R and 2R. So we are repeating this unit, R2R unit, in a ladder format. We can form a digital to analog converter. So that is what is called the R2R ladder digital to analog converter, which produces a corresponding output value, the analog output value, which is equal to the digital input which is connected to the R2R ladder network, this network also will be defined, will be designed using a inverted summing amplifier, which we are, as we seen earlier. So it is very easy because we only need to have two type of resistors, one R and 2R. If you have a 1K resistor, we need to have another 2K resistors. With this combination of these two resistors, we can have n-bit digital to analog conversions. If there are more number of bits present in the digital input, we need to use more number of R2R units. This is how the R2R network will be designed in a R2R ladder network. We can see that looking at each point, the right hand side, this is the equivalent resistor value. So this is, you can see that at this point it is divided at this node A, it is divided as, if you see here 2R, and this side, the equivalent resistor on this side will be 2R. You can see that how it is. So you can see if you are these two resistors, the 2R and 2R are parallel, right? So since these two are parallel, the equivalent resistance of this one will be if two resistors are in parallel, the equivalent resistance will be this 2R into 2R divided by 2R plus 2R. That will be equal to R. So the equivalent resistance for these two unit will be R. So that is this R. Now this R is in series with this R. So these two R are in series. So this form 2R. Again this 2R and this 2R are in parallel. So that is this is 2R and this 2R are in parallel. So that the equivalent resistance of this side will be R. So this is R. Again this R and this R are in series and this form 2R, and these 2R and these 2R are in parallel. So the corresponding equivalent resistor will be R. So this is how we can deduce the network using this R2R ladder unit. Here you can see the practical network using R2R ladder network, and here on the right hand side of A, the equivalent resistor will be 2R. As we seen earlier, if you take the equivalent resistor of all these unit, that will be 2R, and here there is a 2R. So the current at this point will be divided equally between this terminal and this terminal. So 1 milliampere of current will be flowing through this. So this 2 milliampere become 1 milliampere here. That has to be connected to the most significant bit. That is here we are seeing a 4-bit digital to analog converter. So the most significant bit is D3. And this 1 millimeter ampere is connected through this terminal, and this will be equally divided between this terminal and this terminal, and this will be 0.5 milliampere and this will be 0.5 milliampere, and this current will be equally divided between this terminal and this terminal, because the resistor value here it is 2R, here it will be also 2R, and so on. So you can see that the current value is divided by 2 each through each this unit, and this will be corresponding digit. So this is the most significant bit D3, then this is the second most significant bit D2, this is the second bit, and this is the least significant bit where the current value become 0.125 milliampere, whereas for most significant bit it is 1 milliampere. So whenever this D3 is high, this will be connected here. When D3 is 0, this will be connected to the ground terminal. So similarly for each of this unit, so whenever the digital input is high, it has to be connected to this terminal, otherwise connected to the ground terminal. When all the inputs are connected to the ground terminal, means the output is 0. The output will be 0. So that's how we design the R2R ladder unit, that is the network unit. So the corresponding output current at this point will be, we can see that is D3 by 2 actually, because that is I reference by 2. So I reference is 2 milliampere divided by 2 into D3. So that is the first unit here. Then plus D2 by 2 plus D1 by 2 raised to 2 plus D0 by 2 raised to 3. So this will be the output values depending on whether D3 is high, D3 is D2 is low, depending on that. So we can for the most, if this is 1 means and all other terminals are 0, that will, the current will be I reference by 2, that is 1 milliampere. So this is how we design the R2R ladder network. As I said earlier, this has to be connected to a summing amplifier, that is in the inverted op-amp. So this is connected to the output current I out is connected to the inverting terminal of the op-amp. So this is a summing amplifier. So the summation of the current will be amplified and the corresponding output voltage will be obtained here. That corresponds to our input digital values. So this the output analog voltage here will be depending on whether these bits are highs or low. So that output value, it can be in an equation form. We can see that the V out is equal to minus R, because here we take RF instead of RF, we took R. So that is the feedback resistor, R into V3 into V reference by 2R. So V reference by 2R plus V2 into V reference by 4R plus B1 into V reference by 8R plus B0 into V reference by 16R. So this will be the corresponding analog output. The advantage of a digital to analog converter using ladder network is that we only need 2 resistors, and it is easier to implement, easier to manufacture. The response time is faster, and there is minimum tolerance problem, as all the resistors are that are designed on a single chip. These are some of the example of a digital to analog converters in our daily life, like such as the CD players, MP3 players, and digital telephone, where the output value which we are seeing or hearing is the analog values, which was originally the digital signal. So that was the original digital signal which are converted and outputted to through these devices. Similarly, as a functional generators such as digital oscilloscope, where we see the analog outputs in the form of voltage and pulses, where the inputs are actually digital values. Similarly, for the sine wave generators or square wave generators and so on, this kind of oscillating signals, where also the input value is the digital signals which are converted into the analog value. So in the next class, we'll discuss about the analog to digital conversion. Thank you.